Thanks for that introduction, Eugene. As Eugene said, my name's Keith Perrin. I'm very excited to be here to talk to you about MSC Co-Simulation and where we've been taking some of our new capabilities. You know, we're introducing a new capabilities to the market that we think are opening up some new avenues to improving design simulation. We're very excited. We certainly think they're breaking some new ground in the marketplace. You know, with the engagements that we've had with our customers, they look really promising. We think they're a natural next step for capabilities we've had for a while, but we really think that we're breaking some new ground in here, bringing new capabilities together in these rather new ways. At the end of the day, though, our job is to ensure that our customers are having a great time with our software and that they're getting some value from it. So over the next hour or so, we're keen to show you some of the new capabilities we got and see if they can be useful to you. So let's get started. You know, the first thing that we need to really consider as we get started in this area is what customers really do on a day-to-day basis, what they need to consider about engineering design performance. You know, it's often forgotten and somewhat unsurprising in hindsight, but obviously designs don't operate in one domain. These things that we see our products doing, our designs doing, they're not specific to any one simulation discipline. Now, unfortunately, over the years, simulation tools have matured that are specific to individual disciplines. And frankly, this has been matched by our engineering professions. In fact, we've actually encouraged this. The simple fact is that engineering design performance is a mixture of disciplines. Alas, our designs don't care about the way we're organized. They do have to work, however. So when I ask our customers the above question, do your designs operate in only one domain? Of course the answer is, well, no, they don't. So we've got to do something about that. Somehow we've got to enable these simulations to work together. The next thing, take the next step, the next thing that we need to consider is, well, the more types of simulation that we do across the life cycle of design efforts. Obviously, what we're going to be doing in R&D is going to be different, and a different sort of simulation to what we might do for manufacture, for example. You know, in R&D we might be looking at new technologies or perhaps new materials that we're looking at. Whereas in manufacture, we're going to be looking at the processes that people use to make these things. So obviously an entirely different set of simulation needs. Similarly, with design and usage as well, different simulation requirements at different times at different levels. So what we're seeing from a design perspective is actually mirrored in the life cycle of design as well. So in addition to a simple way to simulate multiple disciplines, we also need a way for our engineers and designers to get hold of the simulation types they need when they need them. Well, sounds rather obvious. So as we go through trying to figure out what we need from design simulation, we have to understand what sort of things that we need to do to really push designs forward and really start to focus on what that means in terms of making a better design. So we typically ask these sorts of questions when get engaged with customers right up front so that we can start to understand what different design criteria, what different design performance criteria characteristics are important for any particular design, and specifically what would that mean moving forward. So when we outline the value of co-simulation, we think there's some key things that we need to provide to customers, right? And I've touched on some of these already. At the end of the day, co-simulation is about modeling more accurate design performance using the interaction between multiple physics disciplines. That idea of holistic performance to get a complete insight into what the designs are doing is quite important. So why would you do that? Well, obviously, increased accuracy and precision is definitely one of those things. Right, today, there's quite a lot of people out there making a lot of assumptions about loads and constraints and trying to link these things together in different ways, using, in some cases, frankly, guesswork. Also, what's not often seen is that co-simulation can make things faster. You know, today, if I were to undertake some simulation in one discipline, I've then got to manually make some assumptions and then manually connect it to another. Whereas with co-simulation, we can automate a lot of that. So things get faster naturally. In addition, we've also touched on these aspects. These simulation types, these tools, need to be readily accessible and readily available to the people who need them. This ultimately allows them to use the tools when they need them, as they need them. Now, finally, we don't believe, as I kind of mentioned already, that anybody else has been doing this before. We think we're quite unique in this environment, linking together some of our tools. Therefore, quite excited. So where does this start? Well, for us, it's a common simulation model that has access to somehow to all of these different disciplines. For us, increasingly, this is Apex. Apex provides a unified tool for the CAE environment for virtual product development. Now, although most of our other tools have a preprocessor, it is in Apex where we can create the basis for a singular simulation model from which we can share information across all of our disciplines. This way we can enable simulation engineers to create and edit simulation models without having to defer to complex CAD model changes. And we're increasingly bringing the tools together this way. Right, a real simple example is MSC Cradle CFD. It has a processor like many of the other tools. Right, so we acquired Cradle about 12, 18 months ago or so. And now we've made some changes so that it has the same underlying modeling kernel as Apex. It also now has the same translators. So this enables Apex and Cradle to easily, and rather pragmatically, share data with each other. Our CFD users that we've engaged with love Apex and the way it enables them to create and edit their simulation models very, very easily, very dynamically, very intuitively. They also appreciate the ability of Cradle to create the CFD specific, say, meshes that they're familiar with in a fairly familiar CFD environment. So it's basically a win-win. You know, if you haven't checked out Apex yet, you really should. It's a very interactive, very unique way of engaging with models, modeling, and simulations. And it provides an easy way to edit models without having to go back to the original CAD system. So, really useful tool. If you haven't checked out Apex, you really should. So, anyway, once we have a common simulation model, we can then start to simulate the overall design performance, right? So, with that said, it's time to talk solvers and solutions. When it comes to actually solving a simulation, there's typically three simple levels we see customers wanting to do. At the basic sort of level down there, chained simulation. This is where the results from one simulation can be used to push to another simulation. A simulation allows us to chain these things together. So the results from one can be used as an input for a constraint or a bound condition, for example, in another. Very commonly done. At the next level up, we have bespoke coupling. Here's where we're utilizing an API to link different types of tools together, usually for some more automated methodology or more something that's perhaps a bit more bespoke to a customer, where they want to embed some of their intellectual property into the coupling that goes on. Then right at the top level here, we've got co-simulation. This is where we, as a software vendor, link our tools together in a rather interactive way. So let's look at some examples of some of these things. Right, so chain simulation. Real simple example here between MSC Cradle, CFD and Nastran. Right, so from within the environment within Cradle, using the UI, we can simply identify an area of interest, a region, and then transfer the loads from that, the results from that region into another tool like Nastran, as you can see here. So we've identified this wing as a region of interest. In this particular case, we've highlighted the pressures and we've transferred those pressures into a data bulk file, which we can then solve for Nastran. You know, from within the tool itself, we can translate not just pressures, but things like forces, displacements, temperatures, that kind of thing. And we can see an interactive way to map these things together from within the environment as well. You know, this sort of very simple analysis, very simple chaining, is really where we see the majority of customers working today. For many, this kind of this level of simulation provides some very reasonable results. So, simple chaining. Taking the next level up, where we've got an API, we can take a step further. You know, for example, we may need to automate a process or detail a specific treatment to a model for a specific use case. You know, a favorite I like to talk about is quenching. Here we have customers using JMAG, for example, simulating electromagnetically induced heating. They then coupled that together with Cradle for the cooling piece. And then the resulting deformation is calculated with Marc, our nonlinear structural analysis tool. So along the way, there's also some proprietary things that they're considering in that particular example. So Cradle, like many of our other tools, has a rich API, a programming interface. It also comes with a fairly rich set of user-defined functions so that we can get at some of the underlying physics in Cradle. Right? So all of these are available through the API, just like many of our other tools, so it becomes possible for us to link Cradle to other tools that also have APIs. What's more, we can also do this through standards. The functional mockup interface is a great example of such a standard. Here we can start sharing performance results and co-simulating to some extent with a FMI with any other toolset that also is based on those standardized protocols that FMI has. So this way we can link together different tools in different ways, in the way we need to. You know, a simple example of that, perhaps, coupling-wise, is provided to us through GT Suite and again MSC Cradle CFD. GT Suite is a leading systems simulation software from a company called Gamma Technologies. It provides system-level simulation. In this case, we're linking MSC Cradle CFD to the component nodes in the overall system designed in GT Suite. And you can see these at the top of this particular slide. You can see particular nodes in each case. So we can drive the loads and constraints from GT Suite into Cradle from a system level model, undertake the CFD, and then push those results back out again. So you're seeing both of these examples go on, right? In one case, we're taking loads and constraints from a system model. In this particular example, we're taking the results from our CFD analysis and pushing those into GT Suite. This way, GT Suite users can consider a very rich level of detail in their overall system design. And it allows GT Suite level users to start bringing together a very holistic and rich picture of an entire system. It's a pretty cool technology. You know, another great example, this time from MSC. You know, in this example, we've linked any CFD code, not just MSC Cradle CFD, to our Nastran Aero-elastic simulation. This link provides an interface between the CFD code and Nastran to allow fluid structure interaction simulations, both static and transient. So the CFD code and Nastran executing simultaneously in exchanging information through the interface during the simulation. It provides a tight coupling between the codes. So this fluid structure interaction that we have going on here will take the results from our fluid simulation on the left and drive those in a very specific way through our API to Nastran on the right. And for those of you who know Nastran's aero-elastic capabilities, you'll know that it's not just as simple as transferring some loads. There's some things we need to do along the way involving pre-processing that need to happen to enable this to work. At a very simple way, you can see that in some of the diagram in the center there, where we've got a CFD mesh, which obviously matches the fluid, and we need to map that to the Nastran structural mesh on the right. So it's a simple example of how we can take information in one simulation and couple it together in a really interesting way with the simulation in Nastran on the right. Taking that idea of chaining to the next level is what we've done with our Aero-acoustic simulation, again coupling MSC Cradle CFD to Actran, our acoustic simulation capabilities that we have here at MSC from FFT. You know, Actran is one of the premier acoustic software solutions out there to solve acoustics, vibroacoustics, aeroacoustic sort of problems. Here we've coupled a transient simulation on the right, on the left, I beg your pardon, to our aeroacoustic problem on the right. So we can use this CFD code on the left to drive noise, MVH problems on the right. In this particular case, obviously, we're looking at a motorcycle exhaust. Now, that level of interaction between CFD and Actran is actually not particularly unusual. We're increasingly bringing together these tool sets in a much richer way. So not only do we support transient simulation, which a lot of people do, but we also support steady state simulation. So here we can do a much faster steady state simulation using some of our SNGR methods, for those of you who are interested, and we can couple these together in a much faster way. So we can get a rougher model much faster. That enables us to hone in on a design idea, and then with the transient analysis actually undertake the specifics of what that acoustic noise might be. So between Cradle and Actram we can finally tune the noise characteristics of, in this case, a motorcycle or any other aspect. So there's a lot here we can do. We've seen a lot of success doing this for customers, whether in the motorcycle world here or, say, for example, in other areas of the automotive or aerospace worlds. There's quite a lot we're seeing here. Again, building on that, some of those examples. Another great example that really starts to demonstrate what can happen when we directly integrate our tools is with ADAMS real-time and VTD VRes. Right, so for those who don't know, ADAMS Multibody Dynamics or ADAMS Motion is our key motion simulation tool here at MSC. ADAMS Real-Time provides us with a real rich capability to simulate things in real time in response to real elements. And together with VTD, our toolkit for the creation, configuration, presentation and evaluation of virtual environments, we can start to bring these two worlds together. So ADAMS live simulation capabilities can drive real-time vehicle dynamic simulation with VTD, a very realistic virtual environment for users to interact with and evaluate their vehicle designs. You know, imagine that applied to autonomous vehicles. We not only have a vehicle that knows where it is and where it's going, but we have a vehicle that can sense the environment in which it's in. We have a vehicle that not only understands how it's going to react to real world, it can actually start to embed some real world simulation capabilities into that. So that level of interaction provides us with a vision of the sorts of levels of interaction that we want to achieve across all of our options and all of our offerings. Kind of lofty, high vision perhaps, but it's what's important and is part of the idea that's been driving us for the latest version of our co-simulation capabilities. In our latest release, version 1.6, we've encompassed what could be regarded as the major discipline areas across all of our toolsets. We've got motion simulation from ADAMS, a world leader. We've got structural simulations from Marc, non-linear structural simulations at that, another non-linear, and of course fluid simulations from MSC Cradle. These capabilities are getting us closer to that vision. And driven by a UI-driven wizard, our users can now link together these critical capabilities in a time-dependent, iterative analyses that allow these disciplines to start to interact with each other. So much more than a simple load transfer, for example, and a lot more intuitive than a complex API programming interface. You know, through this, we're starting to uncover some design characteristics that, well, at a minimum would have been difficult and in many cases impossible. So let's look at some of examples. You know, the interaction between fluid and structures is well outlined by the connection between MSC Marc, our nonlinear structural solution, and Cradle for fluids. Here you can see a couple of great examples of that, right? There's an example of how structure reflects fluid performance and vice versa. The example on the left shows us how fluids can be affected by a structure. You know, you can see this thing flopping around in the breeze, so to speak. The example in the middle, you can see fluttering on that pole as a result of the fluid flowing around it. Now on the right, you can see a really nice example of how that can be used practically. Right? A reed valve. The fluid pushes up the reed valve, allowing more fluid to flow through the chamber, and of course as the pressure changes, the amount of fluid into the chamber changes. What's more, as the reed bends, its stiffness changes, which pushes the valve closed. So ultimately, that's going to reach an equilibrium. In that right-hand example, it's made more complex by the nature of that bending reed. In this case, for those of you who know CFD, you may have also heard of an overset mesh capability that many tools have, and we're no different in that. However, we've got a bit of a leadership. This is an area of some leadership for us. Overset mesh, together with the mesh morphing that's going on here as a result of these structural changes, you can start to get some understanding of the level of fidelity and the level of thought that we're putting in here. We're not just simply transferring loads. We're trying to do everything else around it that can start to enable us to couple these things together. In this case, with overset mesh and mesh morphing. That types of meshing are now, as a result, a couple of particularly strong areas, for example, for MSC Cradle CFD. So three more examples here that continue to iterate on a link between structural simulation and fluid flow. On the left, another example of this overset mesh morphing. In fact, you can actually see the overset mesh in the animation. It's that box in the middle of the box in the middle. For those of you who don't know, by the way, overset mesh, what that allows us to do is when things are moving, as they are in some of these examples, of course, allows us to avoid the need to remesh the problem at every single step of the simulation with CFD. All we need to do is just remesh the local area that is the overset mesh. It allows us to simulate these sorts of simulations much faster than what we've done in the past. It enables us to do some other things too, but this is one of the prime benefits. Right, and another great example in the middle this time is diaphragm pump, right? In this particular example, you can see the diaphragm moving as a result of the change of pressure. You can see also some of the stresses and strains and the fluid flow that's going on. I'll talk a little bit more about that shortly. Finally, on the right, a simple example of a fan spinning and pushing a flow, and a resulting vibration and deformation going on that fan as a result. Simple. So we've talked about structural simulation and fluid flow. Well, in addition to that structural side of things, we're also gaining some new insights for the interaction of motion and fluids. Here you can see a simple tank containing a fluid. The fluid is clearly sloshing around and affecting the motion of the tank. You know, in a simple dynamic simulation, without that fluid motion, we have to start making assumptions about what the fluid's doing and how it's driving the tank. Whereas here, with co-simulation, we can directly link these things together and have the fluid affect the motion of the tank. So the motion that gets described in atoms is no longer simple guesswork or an assumption, it's the real simulated thing. Another great example, gaining more practical, perhaps around system modeling. Here we can start to view a slightly more complete, holistic view of system performance. You know, traditional motion simulation, as we said earlier, has to make some assumptions about the forces typically observed by the elements interacting with a flow. Great example here on the screen, right? With flaps on a wing. Obviously, as the speed of the plane changes, the shape of the wing changes as well. And that obviously affects the pressures and forces on the wing, which affects the fluid flow. So if you're designing a motor or a pump, or if you're designing one of the structural elements in this wing, it's obviously fairly important that the engineers are measuring fairly realistic forces as much as we can. And not only that, but they're also understanding how those forces interact with each other. So in this particular case, we're looking at a wing here. It's going at about a third of the speed of sound. You can see the fluid flow moving from the left to the right. We can see some pressure changes. You can see some interaction between the different parts of the flaps. But we can also see the forces acting upon the joints and the mechanism within, and the joints within that mechanism, beg your pardon. You can also see a simple animation that we've included, so you get to see what's going on. Right, so pretty important. Right? And if you're flying on one of these things, desperately important. Getting yet more practical and frankly increasingly complex, we can start to model the interaction of much broader systems. Right? So a couple of great examples here. Wastewater systems, right, where we're transferring loads to atoms from fluid flow of the objects flowing through the water there. We've got a great example here in the middle. Full multi-body dynamic simulation of a vehicle, right? Obviously, in a more traditional simulation, this car is going to continue down that center line ad nauseum, right? Forever. Well, you can see in this particular example, we're applying a wind load from left to right. And as you can see, that's pushing the car off that center line. Now, I don't think I need to describe what's happening on the right. That's fairly obvious, right? We've got a car going through a fairly large puddle or a ford. We can start to simulate the interaction of what's going on with the vehicle and the water it's going through. Obviously, some fairly large impact in that case. So pretty simple examples. Right, so lots of examples, lots of insight for sure. However, all of this would be for nothing if we couldn't view the results. So as I mentioned earlier, we've not just been looking at how we couple our solvers together. That's only part of the problem. We've also been looking at how investing in our post-processing. You know, for the past few slides, the more eagle-eyed of you will have noted that we've had a few images that include both stress and fluid velocity, for example, in the same image. In this particular example, that's exactly what you're seeing. You know, in the block on the right, in the center, we've got von Mises stress, right, being clearly shown. You can also see fluid velocity in the same fringe plot. That's because the post-processing solution that we have, particularly for MSC Cradle, can open Nastran results, Marc results, as well as fluid simulation results from Cradle. And we can start to combine those very simply into the same post-processing window. So all the user has to do, in this case, is drag and drop the result files into the post-processor, and they can see these things, you know, whether they've got Cradle or not, frankly. So, great. I can create a common simulation model with Apex, and I can start to link that toolset to the individual disciplines of choice through Adams, Marc, Flow, for example, and I can then start to simulate them with co-simulation, actually do the solving together in an iterative way, and then view the results. So some key elements there, bringing some of these solutions together. So, how do you actually do that though? That's a key question. Right, so from a digital perspective, a digital thread perspective, the first step is to start building a common simulation model. You know, as I've said already, for MSC users, this increasingly occurs in MSC Apex. Once we have that common simulation model, we can then prep that model for the individual simulations in which we're going to be interested in. Right, so in this particular example, we can create an Adams model with one team and a Marc model with another team. Right, the way we've connected these does support that parallel working environment. And we can then create these individual models, get them working in their individual disciplines, and then we can start linking together with co-simulation in that interactive loop. At each stage, the solvers will connect and share information about the simulation that we're running. So the Adams simulation will run. It will then, in this case, swap positional information with Marc, which will then run and swap the force information with Adams. In this way, we'll start an iterative process to share the simulation results from each other. Now, obviously, once the run, it's relatively simple to view the results together individually in each of the individual systems or in an integrated way, as we just outlined in our post-processor. So that provides a real simple way to get best practice there about how our customers have been using co-simulation and how they've been getting value from it and how they're trying to and choosing to use our co-simulations together. So, I wouldn't take our word for it. Let's spend some time finding out what our customers and the rest of the industry is saying. So if you've got a cell phone now, particularly one of the better ones that can read QR codes, I suggest you pop that onto, fire up your camera and use that to get to the link to the QR code here. For the more adventurous of you who can type fast, maybe even make a note of the URL. In these, on this website, there's a real couple of nice examples. Now I'll bring up the website so you can see it. So this is where that will take you to. Let's see if I can move this out of the way so you can still see. No, so we'll come back to that QR code slowly. But on our MSC website, you can see real nice, good examples here. An outline of things like Apex we've been discussing. Outline of the benefits we think you might get. Some of the key technologies. There's the CoSim engine, for example. Our other open CoSim solutions, chain simulation, real nice example there. And then a whole bunch of examples and a whole range of different areas. So I'm just going to shrink these up so we can see some of them in one place here. Oops. So let's see, what have we got here? We've got fluids, multibody dynamics, structures controls, 3D environment there with multibody dynamics, discrete elements, 1D simulation. So some real nice examples, some of which I've just been through, obviously, right? A whole bunch of good examples there. Fluid and structures, many of the examples. Nice propeller there showing some cavitation as well. quite like that one of my favorites. Great examples here, multibody dynamics and structures, right? We can see ATV interacting with a wall here, bollard impact, nice wiper blade mechanism there for the more adventurous of us perhaps. Adams and Marc here, some non-linear analysis going on between a rubber and a tire and a coiled spring and a suspension. Great example here from Adams and MATLAB Simulink. I mentioned Adams real-time VTD, so we can cover that. Oh, great example here from Adams and EDEM. You know, here in this particular case, you can really see what's going on with EDEM, right? I'll talk a little bit more about these guys in a second, but EDEM do discrete element modeling, right? So the interaction of different particles. And then you can see this ATV, which is an Adams simulation, fully gimbaled Adams simulation with all its suspension and drivetrain, driving through those particles that EDEM simulate. Right? So you can see in here, as it goes through, it's actually pushing some of the particles in the way. The powertrain is going to have to work a little bit harder to get through that. The suspension is going to need to update. It's a real nice example here. I mentioned GT Suite from Gamma Technologies here and Cradle and how they interact. I talked a little bit, well, quite extensively here about acoustics and what we've got going on between Actran. Some real nice example here between Adams and Astran and Actran as well. Great example for electromagnetics and acoustics here between Astran and Actran. And then finally, the example that we had from fluid acoustics. You know, some really good examples here to get to grips with. And one of the nicer areas actually is this white paper. I'll open it here, already got it open. Apparently anybody called Keith has a high interest in multiphysics simulations and co-simulation. Here's one of my namesakes here, Vice President of Marketing, Keith. Also outlining some of the capabilities I had, going into some more technical depths should you need them, about what we're actually doing in some of these areas. So real good, interesting read, right? So, oh, there's a nice example, right? SE Stream providing thermal analysis results to Nastran so that we can start to predict thermomechanical stresses in electronic components. Right, real nice example, right? So awful lot of great capabilities here, so you don't need to take our word for it. You can actually see what customers and the rest of the industry is doing. So with that in mind, here's a great example between Volvo from Volvo with Adams and Marc. Some great practical insight they've been getting around some of their suspension design. And as you can see, real nice quote from Anders at Volvo. You know, here they're looking at curb strike and the interaction of dynamic motion with some non-linear structural deformation that could happen with their suspension, as well as some MVH problems, right? As this suspension, well, as the wheel goes over some fairly aggressive lumps, bumps and whatnot, with curb strike in particular, that's going to have an impact on a good chunk of the car. So here we can start to understand what sort of loads are getting transferred where and how. And we can start to simulate buckling events and stresses and strains on suspension systems that are within that. So quite important way to get a clear understanding of what's going on and how we can simulate those. So it's not just an assumption. We can actually get a fairly rich view of what's going on. In this particular case, when it gets to MVH as well, we can then start to figure out how to get a lighter to suspension, and we can start to figure out things like fuel economy impact as well. So there's quite a lot going on in this one. You know, another great example, which I really like, is from a company called Pratt & Miller, who've done some incredible simulation of a fairly well-known vehicle. I think most of us would recognize this guy, right? As you can see, again, this involves some co-simulation with one of our partners, EDEM, right? I just mentioned those. We've got some great capabilities for discrete element modeling, which I just mentioned. Do a great job of simulating soil, dirt, terrain modeling, etc. Right, so we saw an example of that actually in motion earlier. Right, so this allows them to not just simulate the vehicle in a very simplified virtual world. They can actually model the terra mechanics of the vehicle in a fairly rich way. And it can start to virtually put Pratt & Miller's vehicles through some vigorous off-road simulation that's fairly realistic long before these things are put in the field. And for the folks who have to ride in these, I think that's fairly important. So that process of co-simulating between Adams, in this case EDEM, D-E-M, really gives them a real rich added dimension to the procedures they've engaged with so far. It's a real nice, real good example. Now, in this case, we've also been working as well with a consortium of customers, in this case, working together on some research. So in this case, MSC has been working together with BAE Systems and Sterling Dynamics around NATEP. NATEP is the National Aerospace Technology Exploitation Programme here in the UK. It's a programme to help drive forward key technologies in the aerospace market. In this particular case, we're modelling the fluid interaction with co-simulation in all three of the ways we just mentioned. We've got a simple load transfer going on between Cradle and Nastran. We've also got an API-based coupling for CFD to Nastran's Aero-elastic simulation, which I just mentioned earlier. We've also got a direct co-simulation connection with Marc that we've simulated as well, so that we can start to compare some of the results. And here you can see some of those. We're using results like that to start providing guidance to our customers about what's best for them in the case studies that they have. You watch out for a white paper on this particular one shortly. Real good example. And finally, if that weren't enough, some of our very own team have been driving our simulation technologies, we believe, to the absolute maximum possible. Honestly, with some more social media oriented fun. In this case, the Oscars were underway recently, and our team, in their depths of depravity, wanted to see what would happen to the Hollywood sign, given some extreme wind conditions going on in downtown LA. We simulated the wind coming in from the left to the right, which apparently is a prevalent wind condition in the Hollywood basin. We simulated the effect of the wind and the structural conditions as a result of that on the Hollywood sign across each of the letters as the wind flew across them. And as you can see, the H and the O are experiencing, perhaps not surprisingly, a slightly different set of conditions than some of the rest of the sign. Glad to see us really driving those capabilities forward. Irrespective of that, we're seeing a lot of interest here, not just from customers, some of which you can see quotes from on this slide, but also from our partners and frankly the rest of the industry. We're seeing a clear need for this. It's clear there is a need for this. As I said earlier, designs don't just operate in one domain. As one of our partners puts it, Data Advanced down there in the bottom right, it's clear that the days of isolated simulation of singular physics phenomena is increasingly an obsolete concept. Well, when I consider the designs I've ever worked on, I have to agree with him, right? I just want my design to work. I'm less concerned about the individual physics of any particular discipline and really concerned about how my design works. So, a lot of good examples about what's possible and some great insight into what folks want and need. So, practically, how do you get started? Right, a great question. Because I didn't just talk about linking different physics together, and it's a bit more than just getting a fancy model in a preprocessor or looking at some pretty fringe plot. There's some practical things that we need to do to get started. For us at MSC, one of the first things that we did was look at our MSC One token licensing system. Right here, it's absolutely critical that we're able to leverage this for our customers. We think it's an important tool because it provides access to all of our tools to our customers at any one point. MSC One, for those of you who don't know, provides a single pool of tokens that you can use across all of the MSC softwares. When you use one of the tools at MSC, it pulls the number of tokens from the overall pool of tokens that you have available, and when you close the application, the token goes back to the pool. So pretty simple, right? This way, people can use whatever tools they need when they need them. You can use them for Nastran 1 minute and Cradle the next, or use them for both. It's really their choice. This gives our customers the ability to get the tools that they need as they need them. It really is that simple. What's more, because it's token based, you can scale up the tokens as much as you need, right? The tokens are leased, so you can use them for as little as a week or as much as a few years if that's what you want to do. You can increase the number of tokens you have, or you can decrease them as well. And since it's related to, frankly, how many users you have and how much you use the tokens, the amount you need is more closely related to the amount you actually have going on at any one point. This allows you to flex your usage of the tools to match your needs. Great news is, from a co-simulation perspective, this saves a huge amount of money. Imagine if you had to buy each and every product for each and every discipline. You'd soon find that one of the biggest obstacles to simulating wasn't an understanding of the physics or your expertise perhaps, It's the fact that they're just too expensive. With MSC One, you get access to them all at a fraction of the cost that's traditionally associated with software, right? So traditionally, you have to buy each of the tool sets in each of the discipline areas, and that assumes really peak utilization, and nobody's using all of these tools all of the time. That's ridiculous. With tokens and MSC One, we can start applying those tokens much more reasonably across all sorts of different tools. So for the amount of tokens that you might use, say for Actran, you can also run Apex and Astran, or even Cradle. So that assumes mean utilization, and MSC One also gives you access to all of the other MSC tools. It's a much smarter way, we think, of allowing customers to get access to our software, and it's particularly applicable for co-simulation. Yeah, for us, this is some of the essence of manufacturing intelligence. It's not just good enough to technically link these things together. We've got to give people access. So that's a great start. Getting people access to the software, it's a great start, but it isn't enough. Experience and expertise is, let's face it, another challenging area. Let's be honest, there's not that many folks out there who know all of these tools. So, while we've enabled a way for the tools to work together across the different disciplines, to enable teams to work together in a coherent manner with co-simulation, we're also making our team available to folks when they need to get started with co-simulation. Right? We believe that we've got some of the industry's most experienced personnel, bar none. And as a result of that, we've got some great customer satisfaction and a really high renewal rate with our products. And it's because we're quite focused, as I said at the start of this presentation, on enabling customers to succeed. That's what we're all about here. When we do talk to our customers about how to get started, there's typically 3 areas that we can help, right? So sure, we can throw the software at you because you've bought MSC One. Most of our tools come with training, either in box or in the community that comes with MSC One when you access our tool sets. And there's a whole bunch of online courses and personnel that you can get access to. Now that's fine, but most people don't get paid to learn software. Most of the customers I speak to are actually being paid, to do some engineering. Now, at the other end of the spectrum, on the right-hand side, we've got simulation services. Now, that's nice, right? We've got a whole bunch of smart people who actually do real simulation work for real customers on a daily basis. Now, that's nice. You can imagine, high degree of professionalism, we know what we're doing. But the trouble with that is that it doesn't really give you the knowledge of what you need to succeed, which is why we tend to focus in the center, right? A jump start. Here, once we understand a particular use case that you're trying to achieve, usually through a simple briefing, we'll then start to put together some training for you specific to that need. Typically it's about 3 days, and then over a period of some period of time, usually a couple of weeks to a month perhaps, we'll get that particular use case sorted out for you, and we'll provide you with a follow-up report. Typically we're looking at training costs here. So the great news about this particular effort is when we do it this way, even if you haven't bought the tool set, you get a real good understanding of what the tool's capable of. You also get a good understanding of how that tool is going to fit in your processes and whether it's appropriate for you to make a decision moving forward. So it's a great way to get started. We also insist on real use cases, so no contrived benchmarks or academic studies. We tend to look for real problems that you're really trying to solve. So at the end of that jump start, you'll have some actual solutions to actual problems you really have. A great way to get started with any tool set. So, 3 ways we can get started. With the jump start, you definitely get a win-win. So, a simple challenge to our customers and prospects, right? We believe we've got some of the industry's best technologies. We believe that we've got some of the industry's most experienced personnel. And we believe that we've enabled us to start linking together our tool sets in a rather innovative and unique way that frankly nobody's been able to touch in the real world. So we're encouraging people to get involved with us on a real project. We're pretty positive we're going to get some real results within a short period of time. We're quite confident about this. The capabilities that we're seeing around co-simulation in particular are showing a tremendous amount of promise. So if you like what you've seen and you're curious, we'd like to invite you to try our software on a real project. You can use your cell phone to get access to us on the left there with the QR code, or if you're feeling adventurous, simply email me or Yijin at mscsoftware.com. We're hopeful that you enjoyed the last 45 minutes or so, and we're hoping that you can get involved in a real project with us soon. Thanks for your time.